our session. The first speaker is Jorge RUEDA, and they will tell us about binary-driven hypernovae and the understanding of long GRBs.
Good morning, everyone. First of all, I would like to thank the organizers for this very nice meeting, to allow me to present the results of on this topic, which we have been working for a few years. So I would like to present first, starting as a sort of a historical sequence of our work on this topic. So this our collaboration. It's a big group. Sorry if I missed someone. I hope I didn't. So let's start. Data from gamma ray bursts increasing. We know that, and we heard this morning from Bin Sang how for each crucial observation from gamma ray bursts have been, for example, rule out hundreds of models at the beginning when they were discovered, and then with the observations from Beppo-Sachs and the discovery of the cosmological nature of gamma ray bursts. But data continue to arrive, and now we have a lot of data from the X-rays to the gamma rays, but also from the optical, and we have also from the radio and infrared, ultraviolet, and so on and so forth. And well, with this increasing of the quality, not only of the amount, but also the quality of the data, we now know that gamma ray bursts are much more complex than we thought before. And this is only one example. You can see this is a light curve of a gamma ray burst. It's not a schematic. This is a real data. Just I didn't put the units just for simplicity, but you can see gamma ray bursts showing, for example, these precursors and different what we call actually episodes. So we call this A, B, C, D, episodes 1, 2, 3, 4. You can see this in X-rays, these things, for example, these precursors in the X-rays, then going to the gamma ray from emission, and then it continued to fall. Now we see some other episodes, X-ray flaring, gamma ray flaring, just after the prom emission. Then you see the late afterglow, which show some very nice properties, which will be discussed by Remo Ruffini after my talk. And here you see also the appearance of supernovae that we know from 1998, associated 1C supernovae associated with long gamma ray bursts. So data are increasing, but increasing for the long GRBs, but also for the short GRBs. And with this amount of data, well, we have seen an increasing role of the binaries for the explanation, for the understanding of gamma ray bursts. So actually, this is an old table with 7 possible families of binary progenitors leading to gamma ray bursts, both to leading to long GRBs in the first 3 subclasses, and then all classes of possible short gamma ray bursts. So these binaries for different kind of progenitors, and I will focus only on the first 2 of these subclasses. There is now a new class which was introduced on Tuesday by 1U on the possible low luminosity gamma ray bursts from white dwarf binary mergers. So on the first 2 subclasses, these X-ray flashes and what we call binary-driven hypernovae, just long gamma ray bursts associated with supernovae. They have different properties, and for this system, we propose this picture. So this is a typical binary evolutionary scenario leading to the kind of these binaries that we think can explain this process. And this is actually, I think this is very beautiful plot, as Bing San was introducing this morning. Beautiful plot. I like very much this one, because this is an evolutionary scenario that it was actually already introduced, something like that, for the understanding of the formation of compact binaries leading to short gamma ray bursts. But what is new here? What it is new in this binary scenario is that at some point, after, for example, in the common binary evolution, for example, of a low mass X-ray binary, then it might be possible to form tight binaries composed of a carbon-oxygen core and a neutron star companion nearby. But nearby, I mean something like minutes, orbital periods of the order of minutes, from minutes to half an hour or so. And at the moment of this second supernova explosion in this binary evolution, then usually this goes directly in population synthesis analysis, goes directly to this point. That this supernova, of course, supernova leads to neutron stars. And so this is a common scenario for the formation of double neutron stars, for binary neutron stars, that then, by emission of gravitational waves, shrink the orbit and make neutron star binary mergers. But in between, what we have now, this is the system we are investigating, that we have studied for some years, is that this supernova explosion in a binary system, a supernova with a neutron star companion, can produce actually long gamma ray bars associated with the supernova. This is the supernova that is associated with the GRB. Is exactly this one that is exploding here. So the scenario is like this. So with this explosion you see here, this is a scheme, and you see where you see the collapsing carbon-oxygen core, and of course the supernova explosion. You have the ejecta expanding. And here is the neutron star. You see neutron star is going around the carbon-oxygen core. The presence of this neutron star, the neutron star has a huge gravitational field, so it attracts particles, it attracts part of this ejecta of the supernova, so it will be created a huge accretion, a massive accretion process onto the neutron star companion. This accretion process is actually, it can be shown that it's hypercritical, so it is highly super Eddington, thanks to the emission of neutrino and antineutrino near the neutron star surface. So actually, this you see, this is zoom of the region inside the gravitational capture region of the neutron star. So the matter starts to fall into the gravitational field of the neutron star, and it increases its temperature and density near the star. And so there is a hydrodynamic process going on, and near the neutron star you get actually conditions for neutrino and antineutrino production at huge rates. So this is what happened near the neutron star. This is actually, you see this line here. So it's for accretion rates, which is the numbers we are speaking about. When the neutron star is in a binary system with this supernova, with an orbital period of 5 minutes or so, for example, it can create an accretion rate up to 10 to the minus 2 solar masses per second. So this is a huge accretion rate. For longer periods, of course, the accretion rate is lower and lower and lower because it depends on the density of the matter, and you put the density of the supernova arriving, and if you put the neutron star at far distances, then the compression of the matter of the ejecta, so you have lower densities and lower accretion rates. So this is the typical accretion rates we have in our systems. So this is from 10 to the minus 8 solar masses per second all the way to 10 to the minus 2 solar masses per second. As an example, you see here, this is the temperature that you develop near the neutron star surface for this kind of accretion rates. This takes into account the hydrodynamic process that if the matter falls into the neutron star, it shocks the neutron star surface, and you create this sort of accreting atmosphere around the neutron star, and you create this kind of temperatures. Which is the accretion in this process? There is a dominant neutrino-antineutrino production process, and that is electron-positron annihilation. And this is what you see here, that our systems sit in this temperature density diagram. They sit somewhere here, completely dominated by the neutrino-antineutrino production by electron-positron annihilation. What does it mean? So you have here some numbers, and well, you can go to the reference for additional details for this kind of simulation of the neutrino emission. But what you have is that you can develop a huge release of neutrinos of the order here for the same range of accretion rates, 10 to the minus 8 solar masses per second to 10 to the minus 2 solar masses per second, neutrino luminosities of this huge like this one, 10 to 48 to 10 to 57 MeV per second. So in erg per second, you just reduce by a factor of 1,000,000. So you go from 10 to 42 to 10 to 51 erg per second of neutrino luminosity. So a huge amount of neutrinos going, and they are the responsible for the continuation of this accretion process, because they actually are the responsible, are the carriers of the energy that the material gains from the gravitational energy that is gained during the accretion process. So they release the energy. The photons are trapped in the system. The system is opaque to the photons. They are trapped within the flow, but are the neutrinos which release the energy. And that's why you can actually go highly super Eddington. This is why this is called hypercritical accretion process. So these are the kind of luminosity. So you actually you can imagine what is going on in this system already. But so you have this neutron star accreting. So we have to know how the neutron star increase its mass, because we would like to know, which is the issue here, that we would like to know if this neutron star, by gaining mass in this accretion process, can or not form a black hole. This is a key issue here. So we will have a dichotomy of systems in which the accretion process is enough to lead to a black hole, to a gravitational collapse of the neutron star, and in some other system it will not happen. Okay? But we have to know this. We have to introduce the physics of the neutron star to know. We have to know which is the critical mass of the neutron star. All of you know that we don't know which is the critical mass of the neutron star. But we have to put something so we can evaluate also for different equations of state the fate of this system, of course. This is just to show you. This is equation of state typical from relativistic nuclear mean field models, but you can do the material falling in, then you have to follow the evolution of the neutron star, taking into account of cardinal relativistic effects and also rotational effects of GR, so you have to integrate the full equations, but it's important here is this. This is the relation between the baryonic mass and the gravitational mass of the star, both for the static stars and for rotating ones. This is important because in this case you have to follow for this baryon that you throw into the star. This is its mass and the amount of angular momentum that it has. Then you know how the neutron star is evolving. And this has also a feedback into the simulation of the neutron star, of the accretion process itself and the evolution of the ejecta and all this. This is what we are going to show now in a moment. This is the typical stability region of neutron star. So you see the green line, the Keplerian mass shedding sequence, but the important line for the formation of black hole is the black one. This is secular asymmetric instability region. The red line below is the static sequence. So inside this region, you have all stable neutron star possible. And the important point is to know how the star, starting at some point, start to accrete mass and angular momentum, and how it moves, and where is the fate of this star inside this diagram. These are first simulations, 1D simulations, spherically symmetric, that we did a few years ago in collaboration with a group of Chris Fryer at Los Alamos. So we start from the profile of a supernova explosion, and then it evolves. It was evolved in homologous expansion. This is typical profile already when the material is expelled. So you see, you start from more or less the material at the base of the supernova ejecta. It has something like 1,000 kilometers per second, and it can go all the way up to the border. I mean, the outermost layer can move at 10,000 kilometers per second or 20,000, something like that. You have already the density profiles. You start from that, and these were the first computations, just to show you that indeed for tight orbits, you can reach even up to almost 10 to the minus 1 solar masses per second of accretion onto the neutron star. So this was something like the first computations that we did. I will move fast to introduce bit by bit what we have done. Then we introduce the angular momentum. So something like 2D computation. These were this is the first result of this. IGC stands for induced gravitational collapse. So of course we refer to the neutron star. So you can see here for a short period you have the neutron star in gray. It goes around the core, and the reds are these are the velocity field of the ejecta of the supernova. This is a recent one in 2016 that we start to make a first three-dimensional simulation of this process here in Rome. So you see here the black point is the neutron star, and you see the material of the supernova expanding. And the first two figures you start is time zero, of course, and then you see something like 7 seconds after this system, already the neutron star starts to engulf matter. And this is the typical accretion rate onto the neutron star as a function of time that you get in this kind of system. This is for 2 different binary periods, 5 minutes and 50 minutes. And you see in the right panel, you see the tracks of the evolution of that neutron star inside the stability region. So what you see is that in some cases, for different initial conditions, then you can reach, the star can reach mass shedding limits of Keplerian instability, or in some other cases, it goes to the interesting boundary for black hole formation. I mean, the secular, this kind of stars that follow this path here, arriving. I don't see the green point. The color, this orange or yellow cure, vertical, almost vertical there to the right. So these are the stars that collapse after gaining this mass. This is we show here the same. This is a summary of this system. What will happen? You see the plot of the right. You see like the dichotomy I mentioned at the beginning. Some systems will form the neutron. In some systems, the star gain enough mass and form a black hole. And these are the systems that we call binary-driven hypernovae. So in this system, this amount of mass forms neutron star. The neutron star companion becomes a black hole, and at the center of the supernova, neutron star is formed. So this system for neutron star black hole binaries. I will come to this point after. And on the right of this dashed vertical line are the systems in which the neutron star does not gain enough mass. And so they form neutron star binaries if the system is not disrupted by the explosion. So this dichotomy is very interesting because these systems have different signatures. So this, of course, depends on the orbital period of the binary system. This here we start to see interesting things, because what happened? You see at the beginning, the explosion of the supernova was completely spherically symmetric. We assume a spherically symmetric expansion. But then, by the feedback of the accretion process and of the motion of the neutron star around this material, creates asymmetries in the supernova ejecta. And in particular, you see in this geometry, these are two different systems. In this system, the neutron star creates a black hole. It forms a black hole by gravitational collapse. In the system to the right, it doesn't. But the asymmetries exist in both cases. So the supernova starts spherically symmetric, but then it becomes completely asymmetric. Then I will show additional examples with a better resolution than this plot. This was the initial simulations here in Rome of this process. And you see here the binary. So you see here the black point, where here, this is the neutron star collapsing. This is at the moment of the neutron star collapse. And here you see the other neutron star form at the center of the supernova. Okay? So here you see this was the initial center of the supernova explosion was this one. So you can see very well the asymmetries that this system forms. This has, of course, signatures, both the X-ray and gamma rays and so on that I will mention in a moment. This was the first example we show in that work of an X-ray flash on a system in which the neutron star does not form a black hole, and we apply this for the explanation of the GRB 060218, just to show you these X-ray flashes are also called low luminosity GRBs, low luminosity long GRBs associated with supernovae. So here, yes, we show just the capability of this scenario to explain the X-ray emission observing this kind of system. Also not only, but also explaining from the feedback from the feedback of this initial, of the accretion emission from the supernova, from the accretion process, this energy goes also inside the supernova remnant, and it's can explain the light curve in the X-rays, but also it causes differences in the optical light curves from the supernova, and this is what you see here. Difference in accretion powered supernova and just in only nickel decay supernova. So we are here at this point. This is some sort of three-dimensional view of what is this, how the supernova ejecta looks at the moment of the gravitational collapse of the neutron star. So I will focus from now on this kind of system. Go fast, last simulations. So we start more or less, these are now three-dimensional simulations from the smooth particle hydrodynamics code at Los Alamos. And so the same initial condition that we had before, but we have now a better code with better resolution to show what is going on in this system, just to test if our initial guess was okay or initial simulations. So this is how the three-dimensional supernova explosion looks at the beginning. And then we go to this. Okay, this is a view of the orbital plane of this binary. So you can see here, this is evolution of the binary. So as before, initial supernova explosion, spherically symmetric, then the neutron star going. You see here, some material is also expelled, and it goes, it evolves. You could see here also formation of vortices near the neutron star. What does it mean? So you can see here also in this plot, this is the angular velocity of the particles on the orbital plane. So what you can see here is that some of the particles have enough angular momentum to circularize around the star, and it forms a sort of disk around the neutron star before accreting. So it forms a sort of disk-like structure, and they fall into the neutron star field. These are the vortices that you can see here around. What is nice from these simulations is that you can see both accretion to the neutron star companion, but also then you can follow also the accretion from fallback matter into the neutron star forming at the center of the supernova. So we can track both the effects of both stars into this system. But you can immediately appreciate from this plot is that these asymmetries are maintained, the system that I showed you before. So this, also from these simulations, you can see that. This is, you see a velocity diagram just to show you the vortices here. And you can see also that this ejecta, it has not only radial motion, but also it moves around the orbital plane, and this is very important, as you will see in a while. This is just a view from the top of this region just to show you again this is like a structure from around two stars. And this is what we call the fortune cookie morphology. So just to show you a little bit better the orbital plane view. So you can see this hole that this is open on one side, on the right side, on the neutron star, which is collapsing to a black hole. So this is important. So you have in this system a region in which you have very, very poor baryons. And this is very important for the model of GRBs. So when the neutron star collapses and forms a black hole, it is thought that in this kind of situations, if you form electron-positron plasma from this process, this is typical in GRB models to start from electron-positron plasma that expands. As you need in such a system to explain the prompt gamma ray emission of GRBs, then you need that this electron-positron plasma is engulfed poor baryons with respect to this to its energy. So this hole that is open, you can imagine now, it allows to this electron-positron plasma to go away with very high Lorentz factor. But this is, I will come back just a moment. Just to show you, accretion rate as a function of time. Now they are a little bit more complex. You can see for different energies of the explosion, you can see even erratic curves with different peaks. They could be maybe observed in high resolution in the precursor of the GRBs. we don't know yet. And in the other plot here, this is again for different energies, and the comparison with the typical fallback. You will see here from the, let me see if I have maybe another plot. Yes, here. For different orbital periods too, you can see there is a sort of a scaling of the accretion rate with the orbital period that can follow. And we also explore the possibility of asymmetric explosions, where you can see this asymmetric explosion, the orbital plane. It creates an eccentricity in the orbit, and you can see something like this kind of peaks when the neutron star, the star goes and then goes out the material and re-enters, and it goes, and this goes ahead in this process. Well, this is orbital separation evolution, of course. The orbit cannot stay the same, so it can widen, or it can become, the orbital period can become shorter, and the orbit can also be tilted, can become tilted in the case of asymmetric explosions. These are tables which shows, you can find this in our work. We showed which system becomes, the neutron star stays stable, in which system it collapses to black hole. You can see this in our table. This is just an example. This is just the same I showed you before, that the system stays, some systems state, the systems which are more compact, they state as binaries. All the other systems become disrupted. So this is what's shown in this plot. This is just semi-major axis, and as a function of the orbital period. This is the three-dimensional view, a summary of the three-dimensional view of this kind of system. You can see the hole here, and this is, I focus in my presentation on the orbital plane view. You can see, I think that Remo Ruffini will speak a little bit more on the possibility also these systems which are viewed from the top on this of this kind of binaries. And this is a last slide, just to show, maybe I will show this one, that from the GRB lightcurves, actually what we are looking at, and Remo Ruffini will show that we can see actually this electron-positron plasma going in one direction with pure baryon load. It can escape with very high Lorentz factor. But what happened to the other part of the plasma, which goes in through the ejecta? It experienced a different path, a different evolution. And what happened, actually, you can see this is the moment of collapse. This is the distribution of matter around this site. Okay? So you can see the deep region of very low mass, baryon mass. So around this region escapes the plasma with high Lorentz factor. And in the other regions, what happened is that actually when the system actually escapes, when this plasma escapes and reaches transparency, near the surface of the ejecta, it has only gamma Lorentz factors of the order of 2, from 2 to 5, roughly. And this simulation, if you can see details in the parallel session talk of David Melon-Fuchsman and Remo Ruffini talk. And this is last.
Thank you. Questions or comments? Yes, there is one in the back, maybe. Maybe there are two. I don't know how to. Where are you?
Thank you. George, can you explain again why the emission of neutrinos can help in the accretion of matter?
Yes. Okay. They help because in this kind of plasma, you know there is the Eddington limited accretion, and this is known. When you have this accretion process, you have gain of mass, and you have a radiation coming out from the system in form of photons, for example. And these photons, they exchange momentum with the flow, and they exert pressure on the system. So at some point, they have a lot of pressure, such as a high amount of pressure, that they can push out the mass, the inflow, so they stop the accretion. And this is called Eddington accretion. But this is when you consider that the energy is released in form of photons. When you have conditions for electron and for neutrino and antineutrino production, of course they have much less, this is working, yes. They have a much less cross-section, and they have different opacity in the system. And when you have something like 10, in the case of Eddington accretion, limited accretion, you have a limit for a neutron star, something like 10 to minus, I don't want to give you a number, something like 10 to minus 5 solar masses per year, okay, of maximum accretion rate. When you introduce neutrinos, that are the neutrinos that release the energy from the system, you can go all the ways up to 1 solar masses per second for this system. It's just because of question of the opacity. Of course, you have to develop the conditions for neutrino production. In this case, you reach them. You reach temperatures of the order of 30 MeV.
Dear Professor RUEDA, I'm recollecting some papers you referred to just at the beginning of your talk, published at the beginning of 70s by your director, Professor Ruffini, and some of his co-authors of that time. Between them were Vishweshwara, Breuer. That papers were very mathematical, they can refer to mathematical physics because there you had many sophisticated calculations of parabolic cylinder functions, transmission coefficients through a parabolic barrier. Actually, you have evolved to a kind of very close to observations, astrophysics of neutron stars and black holes, and you almost can give a very good and exact recept of what stars can be evolve to a black hole, what stars can evolve to a black hole. How great are general relativistic effects in your actual research? Okay. Thank you very much.
Okay, thank you. Well, how big are the general relativistic effects that we take into account in our simulations? The most important one is the geometry near the neutron star that changes with respect to Minkowski one, so from the Newtonian case. So it has effects on the temperature, on the density profile near the neutron star surface. This is one effect. This is an effect that depends on the compactness of the star. This is taken into account in our simulation, and the other one is the difference between the accretion of baryonic matter and the actual increase of the gravitational mass on the neutron star and its rotation rate. So these are the two effects, and of course also the fact that when you have the circularizing matter near the neutron star, in most of the cases it states there is a gap between the neutron star surface and the last circular orbit near the star. This is also general relativistic effect that is also taken into account in our simulations.
Okay, I think we can thank Jorge again. Perfetto.